A massive solar storm, the strongest in 2 decades, recently struck Earth, creating breathtaking displays of the northern and southern lights. This event was triggered by a cluster of sunspots 16 times larger than Earth, which released multiple X-class solar flares and coronal mass ejections aimed at our planet. These emissions resulted in severe geomagnetic storms, reaching the highest intensity level of G5, the most intense since the 2003 Halloween storms. Consequently, the auroras extended much farther south than usual, with the northern lights visible as far south as Florida and Mexico, and the southern lights visible in New Zealand, Australia, Chile, and Argentina. The recent solar storms have impacted both space and terrestrial technology. Elon Musk reported on the social platform X that the Starlink satellite service faced issues due to the storm, noting that the satellites were under a lot of pressure, but holding up so far. The storms also disrupted power grids, GPS systems, and high-frequency communications in certain areas. These events suggest that the solar maximum, a period of peak solar activity in the sun's 11-year cycle, might arrive sooner than expected. As the sun's magnetic field flips, more geomagnetic storms are anticipated in the coming months. While these storms could offer more spectacular auroras, they could also further disrupt radio communications and electrical infrastructure. What exactly happened on the sun's surface to cause this geomagnetic storm, and how did it create such stunning displays of light 150 million kilometers away? More importantly, what can we expect when the sunspot group faces Earth again in 2 weeks? The recent solar storm was caused by a sunspot group named AR3664. Sunspots are temporary dark areas on the sun's surface, appearing darker because they are cooler than their surroundings. The center of a sunspot ranges from 3000 to 4500 Kelvin, much cooler compared to the surrounding area's temperature of about 5800 Kelvin. The AR3664 cluster came into view a few days ago, initially appearing normal, but then rapidly grew to 16 times the size of Earth, spanning 200,000 kilometers or 125,000 miles, becoming one of the largest sunspots of the current solar cycle. NOAA's Space Weather Prediction Center issued warnings of increased solar flare risk from AR3664 at the beginning of the month. AR3664 lived up to expectations, emitting a total of 75 M-class flares and 10 X-class flares within a week, accounting for 50% of the X-class flares this year. A solar flare is a sudden, localized burst of radiation on the sun, resulting in a brilliant flash of light across various wavelengths. They can last from minutes to hours and contain tremendous amounts of energy. The light from these flares reaches Earth in 8 minutes and 20 seconds. Flares are ranked by their strength. B-class is the smallest, followed by C, M, and then X, the strongest. Each class is further divided into a scale from 1 to 9. C-class flares are generally too weak to affect Earth significantly. However, M-class flares can cause short-term radio blackouts at the poles and minor radiation storms, posing potential risks to astronauts. Many people confuse solar flares with coronal mass ejections, CMEs. A CME is a vast cloud of magnetized particles ejected into space from the sun. These eruptions occur when the sun's magnetic fields realign explosively, propelling solar material into space. CMEs can travel faster than 1,000,000 miles per hour, taking up to 3 days to reach Earth. Unlike solar flares, which are bright flashes of light, CMEs are massive fans of gas expanding into space. When a CME interacts with Earth's magnetic field, it can create currents that drive particles toward Earth's poles, resulting in auroras. While both solar flares and CMEs arise from the sun's magnetic field realignments, they differ in their emissions, appearances, travel methods, and effects near planets like Earth. Solar activity started to increase on May 3 with an X1.6 solar flare. Over the next 48 hours, 2 additional X-class flares were detected. The situation escalated when a larger X4.5 flare was emitted from the sunspot region on May 4, releasing tremendous energy. The first CME was observed leaving the sun on May 6. 2 days later, on May 8, another CME was detected following an M8.6 flare. On May 9, 2 X-class flares resulted in 2 more CMEs. By May 10, 4 CMEs were heading toward Earth. Scientists believe the last 3 CMEs combined into a single larger event, known as a cannibal CME, due to their varying speeds and overlapping paths. When a CME reaches Earth, the Earth's magnetic field deflects the solar storm. The magnetic fields couple together, creating a funnel that directs gas toward the day side of the pole, resulting in a daylight aurora. The magnetic fields stretch further back, coupling again and breaking like a rubber band, sending gas along the magnetic lines toward the night side poles, creating nighttime auroras. While auroras are typically green, they can appear as large red glows during intense solar storms due to interactions at higher altitudes. Blue and purple auroras occur when solar particles interact with molecular nitrogen up to 62 miles, 100 kilometers high. Green auroras form when particles interact with oxygen at altitudes between 62 and 186 miles, 100 to 300 kilometers. Striking red auroras occur during intense storms when these interactions happen with oxygen between 186 and 248 miles, 300 to 400 kilometers high. To be visible to the naked eye, red auroras must be at least 10 times brighter than green auroras. Geomagnetic storms can significantly impact electrical power grids and satellite infrastructure. During a geomagnetic storm, geomagnetically induced currents, GICs, can flow through power transmission lines and transformers, causing them to overheat and potentially fail. This can lead to transformer failures, tripped protective equipment, overloaded transmission lines, and damaged generators, resulting in large-scale blackouts. For instance, in 1989, a geomagnetic storm caused a 9-hour power outage for 6 million people in Quebec, Canada. In October 2003, the Halloween storms caused widespread disruptions to satellites and communications, along with power grid issues in Sweden. In 2022, a solar flare resulted in the loss of 40 newly launched Starlink satellites. Currently, the Sunspot group AR3664 has moved behind the Sun's disk, making it temporarily invisible from Earth. This means that any emissions from this group will not impact our planet for the next 2 weeks. However, AR3664 is expected to reappear and face Earth again after this period. Based on observed sunspot behaviors, AR3664 could remain active when it becomes visible again. Just before it rotated out of view on May 11th, AR3664 produced significant solar activity, including an X1.8 and a larger X5.8 flare, the latter associated with a CME. This suggests AR3664 might still generate more solar flares, indicating its activity cycle isn't over yet. AR3664 is an unusually large sunspot, visible from Earth without magnification, though never look at the sun without a solar filter or eclipse glasses. The size of AR3664 is comparable to the sunspot that caused the 1859 Carrington event, the most intense geomagnetic storm on record. The Carrington event caused sparking and fires in telegraph stations, and auroras were seen as far south as the Caribbean and Mexico. In 1859, the telegraph was the most advanced technology. Today, our reliance on satellites and various technologies requiring stable magnetic environments makes us more vulnerable to significant solar activity, like that from sunspots such as AR3664. The increased dependency on electricity and emerging technology today means disruptions could lead to trillions of dollars in losses and risks to lives reliant on these systems. A Carrington-class event today could result in damages ranging from 60 cents to $2.60 trillion in the US alone. Recognizing the threat posed by extreme solar storms and taking proactive measures to protect our technology and infrastructure is crucial. The solar storms in May 2024 suggest that the solar maximum, along with the sun's magnetic field flip, may occur sooner than anticipated. If you enjoyed this video, be sure to give it a thumbs up, share it with your friends, and subscribe to my channel for more content like this. Thanks for watching.